Hello, welcome back to Missogram's Maths. We are going through the worked solutions for the D&D Resources, and we're on Practice External Assessment number 6 from the Complex Numbers booklet. So again, a thank you to D&D Resources for allowing me to use their materials in this way. I have put a link to their website in the description for this video, so you can go online and order physical copies of this book. When it comes to maths in particular, I highly recommend that you do this stuff on paper and not just straight off of a screen. Because a lot of the stuff you can't type out so easily. Okay, so question 1. We've got that x minus 2 is a factor of this polynomial, which if it is a factor, it means that we can put the 2 into it and we'll get an answer of 0. So we'll have a 2 in every place where there's an x, like this, and set that equal to be 0. Tidying that up, we get 8p. We've got 2 squared is 4, and then times the 3 is a 12. Then we have minus 2p plus 4 equals 0. So collecting those up, we have 6p minus 12 plus 4 is going to be minus 8. So 6p is 8. P is 8 over 6, or 4 over 3. Part B, we've got w. We need to find w to the minus 2 and put it onto the Argand diagram. So w to the minus 2 is 1 over w squared. So that's 1 over 0.1 minus 0.3i squared. Now that much we can do on the calculator, save ourselves a bit of effort. So 1 divided by 0.1 minus 0.3 I all squared is equal to minus 8 plus 6i. And then popping that onto the Argand diagram, we go minus 8 in the real direction and plus 6i in the imaginary is going to be just here. For part C, we've got one solution is z equals minus 3, which means if we put minus 3 in the place of z, this equation will be true. So let's start with that. And then that'll help us to work out the A. And then we can go ahead with finding the other solutions. Okay, so minus 3 cubed is minus 27. Times by 4, that's minus 108. Minus 3 squared is 9, so this is 9a. Minus 3 plus 21 equals 0. Okay, so minus 108, take off 3 and add 21. So 9a will be equal to 90, so a equals 10. Now for the next part, let's write in what our full equation is. Now we know that a is 10. We also know that if minus 3 is a root, then this tells us that z plus 3 is a factor. So we can use that to find the other factor of this polynomial. And there's a couple of ways that you can do this. You can do it by inspection, by taking a look. You can use algebraic juggling. You can use long division. I'm going to do it by inspection. So looking at what we would need in the next bracket to make that true. So it'll be something z squared, something z, and then a constant. Now to make 4z cubed, we need to do this z here times by this z squared here, so we'd need a 4 in front of it to make that true. Now the next bit is to look at the constant term. So this constant term here will be 3 times by whatever is in the constant term there. So to make that be true, then that needs to be a 7. So this will be a plus 7. missed there. Okay, now we just need to work out what goes in place of the z. For that we can either look at the z terms or we can look at the z squares. I'm going to look at how to make a z. So to make a z we would do z times the 7 here, and we would do 3 times whatever goes in this z here and add them together. So we would have 7z plus something z has to be equal to 1z over here. So that gap has to be minus 6. Now that gap is made from doing 3 times that space that we have there. So this one must be a minus 2 to make it into the minus 6. Okay, so let me pop in a minus 2 just there. Okay, we'll just tidy this away now. So now we've got the quadratic factor, we can solve that. So we're setting 4z squared minus 2z plus 7 equals 0 to find our other two roots. So z is minus b, which is 2, plus or minus the square root of b squared, so that's 4 minus 4ac all over 2a. Which is going to be 2 over 8 at the beginning part, so that'll be 1/4, plus or minus, and then we've got 16 times 7, and we're doing 4, take away that. So this will be the square root of minus 108 over 8. Now, if we include the 8 into that square root and make it a 64, then we can do some simplifying. Let's see if that helps us at all. Okay, so now we've got 1/4 plus or minus the square root of minus 27 over the square root of 16, so that'll be just a 4. Minus 27, we can take out a square number of 9 there. So we've got 1/4 plus or minus. If we take out the 9, make 27 9 times minus 3, and bring the 9 out of the square root, we've got a 3 with a 3 left over. Taking out the minus 1 gives us the I, and this is all over 4. You can also check that one on your calculator using equation solver. So if we do equation solver for a polynomial quadratic, of degree 3, and put in the cubic that we had to begin with, then we've got 4 in the place of A. We had a 10 in the place of B. We've got a C is 1 and D is 21. We can set up our options to show us the complex roots and then solve it. And you can check that these answers match what we've got just here. They are in decimal form, but those decimals do work out to be the same as this. Okay, for part D, it looks like there's a fair bit we can do on the calculator here, but we must make sure we show all of our steps to be able to reach that merit award. So 1 over u minus conjugate of u squared will be equal to 1 over 1 minus 2i. Conjugate of u is 1 plus 2i, and then squaring that. So this would be, we're going to have 1 divided by 1 minus 2i. So 0.2 plus 0.4i. 1 plus 2i squared and then putting that together, we're going to have 0.2 plus 0.4i take away the answer we just got. Oh, I've put in something wrong. It's just that one there. From there, we need to get out a factor of 8 and 9 from those coefficients there. And using the function on the calculator to turn this into fractions might make this a little easier. So this is 16 over 5 minus 18 over 5i, and we can see some factors of 8 and 9 there. So if this was going to be 8 minus 9i, then from the 16 over 5 we've taken out a 2 on the top and a fifth, and that applies the same for the 18 over 5. So k is 2/5, which is the same as 0.4. Right, for part E, we've got the modulus of this expression is equal to 2. So first we can say that the modulus can be separated into the top and the bottom of the fraction like this. Now if we take the modulus of the top, we've got the square root of the real part plus the imaginary coefficient. It's all squared, each of them squared, added together. And then that's over, again, the real part squared, and we add on the imaginary coefficient squared. So we end up with the square root of k squared plus 9 over the square root of 4k squared plus 1. Now, if we've got a square root on the top and the bottom, that's the same as if we were to say the square root of the whole thing. That's equal to 2. So then k squared plus 9 over 4k squared plus 1 will be equal to 4 if we square both sides. Working that through, bringing the 4k squared up and to the right, we times it by the 4. We'll get a 16k squared plus 4. Now let's take the k squared plus 9 over to the right hand side, or the k squared parts over to the right. We'll have 16k squared minus a k squared would be 15k squared. 9, take the 4 over to the left. 9 minus 4 is going to be 5. So k squared equals 3. K is plus or minus, oh no, it's not 3. Sorry, it's 15. 5 divided by the 15. K squared is a third. So k is plus or minus the square root of a third. That can also be written as plus or minus 1 over root 3. Okay, for question 2a, we are on an achieved question, so I'm going to do it almost entirely on the calculator. So first of all, we'll write P over Q, and we're going to do 3 minus I divided by 1 plus I is equal to 1 minus 2I. So the modulus of P over Q, we can actually do the use our options for complex numbers, and to get modulus, it's the absolute value, so we use absolute value of the answer we just did, and we have 2.236, which is probably the square root of something, because that's what we're dealing with modulus stuff. So if you needed to show it as an exact answer, let's just square it and check what it gives us. It's the square root of 5. Now you probably don't need to express it like that as a achieved question, but it's there as an option if you did come across something like that. Okay, for part B, let's try and simplify each of those surds in that bracket before we go ahead with the cubing, because if we were to cube that now, that would get quite complicated, but let's sort out what we have inside the bracket first. So we can divide by 16. We're always looking for square numbers, and the largest square numbers that we could make into that. And that's because on the next line we can turn that into a 4 root 3. Okay, now the 12 we could take out. The first one has given us a clue because we're looking for things that are root 3's now. That'll help us out. So 12 we can turn into being 4 times 3. So this would be taking out the square root of 4 would give us a 2 root 3. And then 75, if we divide that by 3, we've got 25. So this, if we square root the 25, we've got 5. So that is 5 root 3. So 4 plus 2 take away 5 is simply root 3. And then root 3 cubed is equal to, well, if we do root 3 times root 3 times root 3, well, those two root 3's would make it into a 3. So we have 3 root 3. For part C, we need to get this expression into a more standard looking quadratic. And then we can find the discriminant and set it equal to 0 to make one repeated solution. So let's expand that bracket. On the left, we've got x squared plus 4x plus 4 is equal to kx minus 3. So then x squared plus 4 minus k will be the coefficient for the x, and then 4 plus 3 for the constant, like this. Then we're looking for one repeated solution, which means that the discriminant has to be equal to 0. So then the discriminant on this one, b squared, that's 4 minus k squared, minus 4 times 1 times 7 has to be equal to 0. So 4 minus k squared minus 28 is 0. 4 minus k squared is 28. So 4 minus k is plus or minus the square root of 28. Minus k would be minus 4 plus or minus the square root of 28. So k would just be 4 plus or minus the square root of 28. And then looking at, we need it to be in this form here. We'll just tidy that up. So we've got 4 plus or minus, 28 can be divided by 4. So if I just do that over at the side here, so 28 would be the square root of 4 times 7, so that's 2 root 7. On part D, we've got a little bit of work to do in sorting out these bits and making things equivalent so we can work out the values of A and B. So let's start by rationalizing the denominator on the left. So ai to the 9 minus I to the 4 over 2 plus I. We're going to times it by 2 minus I over 2 minus I. Before I do that, let's just tidy up what's on the top of that fraction. So I to the power of 9 is going to be a positive I. So we can just do that as a times I. And then I to the power of 4 is 1. So we can replace this I4 with a 1. Okay, now multiplying across, we will have 2ai minus 2. Then ai times minus ai squared is minus ai squared plus an I. And on the bottom we have 4 minus I squared. So we've got a minus 2. The I squared with this a just here, so the I squared becomes a -1, times by the minus there makes it a plus a. I'm getting the real parts out first. Then the imaginary, we have 2ai plus I. And on the bottom, I squared is -1. So if we do minus minus 1, we've got 4 plus 1, which is 5. Now let's go back to here and compare it to the 3 plus bi. So for the real parts of that, on the left, on this bit, we've got these are the real parts. So a minus 2 over 5. And the real part in the 3 plus bi is the 3. So then a has got to be 3 times 5, which is 15, and add on the 2, so that is 17. And the imaginary parts on the right, on this the left-hand side of the original equation, we've got that's the imaginary part. So we have 2a plus 1 over 5, and the imaginary part on this is b. So the a we just worked out was 17, so 2 times 17 plus 1, and then divide it by 5. So b is 7. For part E, we are going to set z equal to x plus iy. So then on the left, we have the modulus of x plus iy plus 1 is equal to x plus iy plus 5 plus 6i. Okay, modulus means we're going to do the square root of the real part, which is x plus 1 squared, plus the imaginary coefficient squared. That will be equal to x plus iy plus 5 plus 6y. I'm actually going to rewrite that to collect up the real terms together, so x plus 5, and the imaginary terms y plus 6. Okay, now let's square both sides. Now think about this as being x plus 5 plus y plus 6i, like this, and then we'll square that so we can treat them like two terms, make it a little easier in our working out. So this will be x plus 5 squared plus 2 lots of x plus 5 y plus 6i plus y plus 6 squared I squared. Now that saves us a little bit of effort because we can notice that on the right hand side we have an imaginary term, but on the left hand side we don't. So on the left, if we're just looking at equating imaginary parts, we would have 2x plus 5 y plus 6 is equal to 0. That gives us solutions of x equals -5 and y equals -6. And for each of those two possible solutions, we need to find the corresponding y or x that would go with them. So if x equals -5, looking at this line here, we would have x plus 1 is 6, or no, wait, it's a -5. So -5 plus 1 is -4, and then square it, we get 16 plus y squared is equal to, well, -5 in here, plus 5 is 0, so we'll just have y plus 6i squared. Well, I squared is -1, so that is going to be -1 and then this squared. So that's minus of y squared plus 12y plus 36. So putting that minus through there. And bringing all of this right-hand side over to the left, we would end up with 2y squared. Then we've got a plus 12y, and we have 16 plus 36 is equal to 0. Now if we try and solve that, we can use equation solver at this point. We've got a polynomial with degree 2. The a is 2, the b is 12, and the c is 52. And we solve, and you can see that this has complex roots, which is not sufficient at this point, because we need y would be a real number to be able to put it into z and make it a complex answer. Now this is showing me up as complex roots because I previously had my calculator settings, let's just go back a step, to show that we were doing it in complex mode. If you didn't, and this was just showing it as real answers only, and we hit solve, you'd see there's no real roots. Okay, so this one doesn't work as a solution. No real roots. Okay, so back to if y is minus 6. From this bit just here. If that were true, and again we go back and we pop it into this line up here, we can work out the corresponding x. So if y is minus 6, we've got x plus 1 squared plus 36 is equal to x plus 5 plus, well, minus 6 plus 6 is 0i, so that's going to have nothing there. It'll just be that bit squared. So we've got x squared plus 2x plus 1 plus 36 is equal to x squared plus 10x plus 25. So the x squareds cancel, and we've got, let's bring the x's over to the left, so 2 minus 10 will be minus 8x, and then 25, let's go back to this, so 25 take off 37 is minus 12, so x is 12 divided by 8, 1.5. So we have got a solution there. Now just don't lose track of what we're doing for this question. We're trying to solve for z up at the top just here. So our final stage is to write what our answer for z is. So z equals x plus iy, so that's 1.5 plus the y is minus 6, so that'll be minus 6i. Okay, for question 3, we're solving this quadratic, so I'm going to head to quadratic formula because that's what most people are comfortable with. You could also do completing the square. Right, so x is equal to minus b, which will be 8px plus, or sorry, just the b, 8p plus or minus the square root of b squared, which will be 64p squared, minus 4 times a times c, all over 2a. So 8p over 2 is 4p, plus or minus, we're going to have the square root of, it's going to be 64p squared, take off the other thing there, so 4 times 18 is going to give us 72p squared, so 64 minus 72 is a minus 8p squared. That is all over 2. Now if we sort out what's inside of that square root, to square root the p squared, we can just bring out the p. To square root the 8, we can take out a 4. This would be 4 times, or sorry, minus 4 times 2. Now the 4 we can bring out and make it a 2. The minus comes out and becomes an I. So then we're just left with this being root 2i all over 2. So tidying that up, we have 4 plus or minus, the 2's cancel, so we've got p root 2i. It's a little bit weird to write it that way round. We usually put the number first, so that's root 2pi. Okay, for part B, we've got this division to do and then convert it into rectangular form. Since this is only an achieved question as it's a part B, I'm going to do that on the calculator. So what I'm going to need is some options of what we can put in here. So we've got 6, and then cis is using this little symbol just here, the little angle formula. So we just press shift and then this button. And then we've got pi divided by 15. That's going to be divided by, in fact, I'm just going to put brackets around all of it just in case, just to make sure we've got that division happening correctly. Okay, so then we will divide that by 1 cis of 2 pi divided by 5. And it gives us our answer straight away in rectangular form. If I needed that in polar form, I can do a conversion using this button here. That would turn it into polar. But the answer happens to, the question's happening to ask for it in rectangular form anyway, so that first default answer there is correct. So 3 minus 5.2i, or if I want to be a little more accurate, 5.196i. Okay, we've got a purely algebraic question for part C. Let's start by trying to put this into the same denominator that we have on the right-hand side. So if this is all going over x squared minus 4, x squared minus 4 is made up from doing x minus 2, x plus 2. Which helps us to see what we've got to multiply each fraction by to make it over that denominator. So for the px one, we've got the x minus 2, the x plus 2, we've got to times it by the x minus 2 to make that be equivalent. Oops, let's just fix that up. For q, we've already got the x minus 2 on the bottom, so that gets times by the x plus 2. And then the r, we've already got the denominator as we want it, so that doesn't need to change. It's just x squared minus 4. Okay, now multiplying that through, we will have p times x squared minus 2x plus q x squared plus 2x plus r is equal to 8x minus 3. So now looking at the x squared terms, we have a p x squared plus a q x squared, and we have nothing on the right hand side, so 0 x squared. So p plus q has to equal 0. Looking at the x terms, we have minus 2px plus 2qx is equal to 8x. So minus 2p plus 2q is equal to 8. That gives us something we can solve using simultaneous equations. So we've got two unknowns, and the first one is the coefficient is 1, 1, and then the constant is 0. Oops, not finished yet. And then the second one, we've got a minus 2, a 2, and equal to a constant of 8. We solve that. We've got p is equal to minus 2 and q is equal to 2. And then the last bit is for r. That's looking at the constants of this equation up here. The only constant we've got on the left-hand side is r, and on the right it's minus 3. Okay, for part D, first of all, we need to express this bit in polar form so that we can use de Moivre's theorem on it. Okay, so if we think about what this looks like, we're in the positive quadrant, we're across by k root 2, and up by k root 2 on the imaginary, which puts z to the 4 just here. Now putting that into polar form, we need a length and an angle. Well, the angle is 45 degrees, which is pi by 4. So z to the 4 will be equal to a modulus and then cis of pi by 4. Now the length of it is using Pythagoras, so the modulus of z to the 4 will be equal to the square root of k root 2 squared plus k root 2 squared. So that's going to be the square root of k squared, or rather root 2 times root 2 is 2, so that's going to be 2k squared plus 2k squared. That's the square root of 4k squared, so that is equal to 2k. So our modulus here is 2k. Okay, now on to using de Moivre's theorem to find the roots. So the first root is by doing 2k cis pi by 4 to the power of a quarter. Now the modulus gets put to the power of a quarter, so that's the fourth root of 2k, and the argument gets divided by 4. So this will be pi by 16. Now once we have the first solution, all of the others are equal distance around that diagram. Now if we have 4 solutions because we are doing an equation to the power of 4, we know that those 4 solutions will be evenly spaced around there. So each of them will be 90 degrees on from the last one, which is another pi by 2. So the second solution will be to add on pi by 2, which is the same as saying it's the fourth root of 2k because the modulus never changes. But if we do 1/16 plus 1/2, we get 9 pi by 16. Now the third root, I'm just going to go over and look at the diagram because that's going to end up being over the pi line, which means we actually want to take it under and make it negative instead. So we'll go from this one through there. So this will be fourth root of 2k, cis of pi by 16, take off 180, which is pi. So 1/16 take away 1. This will be 4 root 2 cis of minus 15 pi by 16. Just give myself a little more space for the next one. So z to the 4, fourth root of 2k cis, and this one will be taking us from the first solution just back by one lot, so back by 90 degrees or pi by 2. So that'll be pi by 16 take away pi by 2. So 1/16 take off 1/2. It's going to be minus 7 pi by 16. Okay, last question. So is often the case with locus. Let's start by saying z is equal to x plus iy. Z minus v is x plus iy minus 3 plus 2i. For x minus 3 plus y minus 2i. The argument of this thing places it over here with an argument of 3 pi by 4. Now that is at a position of x minus 3, y minus 2. But the x minus 3 is on the negative portion of that axis. Since this is 3/4 pi, it makes this bit here a 1/4 pi, or 45 degrees, which means we've got an isosceles triangle. So y minus 2 is equal to minus x minus 3 in length. 2 equals minus x minus, plus 3. So y is minus x plus 5 as the locus that we are looking for. So any point that is on this line here is going to satisfy this situation that we had in the question. Okay, that's it for this set of answers for the worked solution booklet for complex numbers. I am also doing the ones for integration and differentiation. If you're looking for worked solutions to those D&D books, check out the homepage on my channel and you'll be able to find what you're looking for.